In this video, I want to talk about the final of Newton's 3 laws of motion. Remember that Newton's first law, which is all about inertia, predicts the behavior of objects that are experiencing balanced forces, which is something we call equilibrium. And Newton's second law explains how net force and mass work together to affect the acceleration of objects that are experiencing an unbalanced force. And we have this very useful equation where the net force equals the mass of the object times the acceleration experienced. And remember that net force or force is measured in newtons. In this case, mass needs to be in kilograms, and then acceleration would be in meters per second or meters per second squared. Newton's third law, then, explains how two objects exert forces on each other. And that sort of the quick way it is stated is the sentence, for every action, there is an equal and opposite reaction. So let's dissect that a little bit. Force is coming in pairs, and we call those action-reaction pairs. Each of the force in an action-reaction pair is actually acting on a different object. So they're not going to cancel each other out because they are not acting on the same object. In our illustration here of a book sitting on a table, we have the weight of the book, which is being affected by the force of gravity, of course, is putting an action force in a downward direction on the table. And the table is supplying a reaction force in an upward direction as that normal force that is a strong and stable support for that book. So our two forces are the downward force being exerted by the book and the upward force being exerted by the table. When two objects interact, such as this book and the table, the magnitude or the size of the force on the first object is equal to the magnitude of the force on the second object. So the amount of force the book is placing on the table is equal to the amount of force the table is placing on the book. But the direction of the force is opposite. So of course you can see that from the arrows. The book is exerting a downward force and the table an upward force. And this is kind of the key word, the key part of this whole idea. The effect of the force on the first object, which would be the acceleration, is not necessarily the same effect as the force on the second object. And we have to use Newton's second law to figure out acceleration. In our book on the table example here, this is a balanced forces situation. You can tell by the equal length of the arrows. And so there's not going to be any acceleration going on. But in most cases, when you have an action and reaction pair happening, when two objects are interacting, there is acceleration, and something or both is going to be experiencing a change in motion. So let's look at some specific examples. Here we have a runner, and this runner is pushing on the ground. So the action force from the runner is pushing down on the ground. The reaction force is the ground pushing up on the runner. The force is the same, but the mass of the runner is very, very small. We'll make a little m, in comparison to the mass of the ground, which of course is huge because you have the earth underneath all of that ground. So when the same force is applied, the object with the smaller mass is the one that's going to experience the greatest change in acceleration, and that's what is going to be seen as this runner moving forward. So it's not the force magnitude that's making the runner move forward. It is the mass of the object involved in this action-reaction pair. If we look at this second example, you have a similar kind of situation going on, but here we don't have a big mass. We have a smaller mass of the boat, and the boat also has got a very low friction surface because it's sitting in water. So if you've ever stepped off a boat, you know as you move forward, the boat does move backwards. And so in this case, the masses are more similar. The boat is able to move freely on the water, and so the force given off by the person pushing against it as their foot leaves the boat will cause an acceleration of both the person forward and the boat backwards, opposite in direction, probably at slightly different speeds. The action-reaction pair also explains why guns recoil. And in the old days, we have a cannon, and you see the cannon is going to have some kind of bracing on the ground. Or if this was a cannon on a ship, it would have many, many chains or ropes holding it. Because as the cannonball is being exploded out the front of the cannon, these expanding gases in the explosion are also pushing back against the cannon and accelerating it in a backwards direction. That's why we have a recoil on a gun, be it a handgun or a rifle, that again, the action force of the explosion pushing the bullets forward is going to then push the gun backwards. So action-reaction forces equal in force size, opposite in direction, and the effect on the object is going to depend on the mass. There'll be some change in acceleration. It may not be discernible, like when you push off against the Earth. Your force on the Earth is just not going to be anything that we could measure because it's going to be so small. But with objects that are closer in size, you can see an acceleration of both objects in opposite directions. So, identifying action-reaction pairs, you just want to think about what two things are involved. So, when a tennis ball collides with a tennis racket, let's say it's going, forward and backward. So the tennis racket's force is going to be applied to move that tennis ball forward. The tennis ball is going to apply a force in a backward direction. Same magnitude, but you've got some differences in masses. And so the tennis ball is going to probably move faster than the tennis racket, along with elastic forces and a lot of other things that get part of that. A bowling ball pushing into a bowling pin, if the bowling ball pushes the bowling pin leftward, well, then the pin is going to be exerting a force in a rightward direction on the bowling ball. But again, you've got two very different masses, so you'll have very different accelerations as a result, using Newton's second law as the principle for figuring out how things are going to change. When a balloon is filled with air so that it becomes a sphere, we have air particles that are exerting a force into the inside of that balloon. So those air particles are pushing on the balloon, and the balloon is pushing back on the air particles, and that's why you have that nice tight feeling of a filled up balloon. And then if you release the air from the balloon and it flies around the room, well, the air is being as it is exiting to the balloon has been pushing, is pushing in on the air, and then as the air exits, it's actually pushing back on the balloon, and so that's what's propelling our balloon forward. It can be harder to identify an action-reaction pair when the second object is not obvious. So if we have an action-reaction pair when a boulder is free falling through space, it fell off a cliff, there's no significant air resistance. Well, what action-reaction pair is involved? What force is on the boulder? Well, if it's in free fall, so I'll just draw my little rock here. It's free falling in a downward direction. So, of course, this is going to be gravity. So the force of gravity is pulling it down. And so we have to have an upward force. So the gravity is being provided by the Earth. And so the easy way to figure out an action-reaction pair is you name your one that's obvious. So the gravity of the Earth is exerting a force on the boulder, and then you just flip the two objects, and you would say the boulder is exerting a force on the Earth. But again, in this case, we've got such a big difference in masses, you're not going to see an acceleration change in the Earth the way you see an acceleration change in the boulder. Kind of a classic example for Newton's third law is found in many physics textbooks is that students are asked to explain if action-reaction pairs exist, how can in this case, a mule or a donkey or a horse pull a cart? Because isn't the action and reaction between the horse and the cart the forces are equal between the two? So how can there be an unbalanced force? How can they go forward? And of course, the trick here is that it's not the forces between the cart and the mule, in this case, that are causing it to go forward, but it's the force between the mule and the Earth. And so we have the animals pushing off against the Earth, and then the Earth, of course, being so massive, is pushing back. And it is that unbalanced force that's going to cause the whole system to go forward. This set of balanced forces between the mule and the cart down the harness just allows them to stay together as one system. So, to check for understanding, can you state Newton's third law that for every action there is an equal and opposite reaction? Can you explain what equal and opposite reaction means and what what each part is pointing to? Can you explain why these action-reaction pairs are not just canceling each other out? Can you explain how you use Newton's second law in conjunction with Newton's third law to explain how these different action-reaction pairs cause different amounts of acceleration in each object? And can you identify the objects that are involved in an action-reaction pair if I give you a scenario?